Welcome everyone and a very good day to all. In this video, we shall learn about digital signals that are used in data communication. The attributes of digital signals such as bit rate and bit length are discussed. We also show how digital data can be sent using analog signals. Baseband and broadband transmission are also discussed in this video. This is the first installment of a three-part video for chapter 3. Here is the table of contents for you to navigate through this video. Okay, let's start with digital signals. First, we have to be clear. Data can be analog or digital. So the term analog data refers to information that is continuous, whereas digital data refers to information that has discrete states. In this video, we shall look into how information can be represented by a digital signal. For example, a 1 can be encoded as a positive voltage and a 0 can be encoded as a 0 voltage. A digital signal can have more than 2 levels. In this case, we can send more than 1 bit for each levels. So we can see here in the figure at the bottom, we show 2 signals. On the left, we have one with 2 levels, and on the right, we have a digital signal with 4 levels. So from there, you can see that 1 bit per level are sent in the 2 levels digital signal, and on the right we have 2 bits per level are sent. In general, if a signal has L levels, each level needs log2 L bits. For this reason, we can send log2 4, which equals to 2 bits, as the digital level is with 4 levels. Okay. Can you try this? If a digital signal has 8 levels, how many bits are needed per level? Any guess? Okay, so we can calculate the number of bits from this formula, and you shall get each signal level represented by 3 bits. Okay, let's try another example where a digital signal has 9 levels. How many bits are needed per level? Can you calculate them and try them? Okay, so if we calculate the number of bits by using the previous formula, we can see that each signal level is represented by 3.17 bits. However, this answer is not realistic. The number of bits sent per level needs to be an integer as well as a power of 2. So for this example, we shall choose 4 bits to represent one level. Next, let's move to bit rate. Okay, most digital signals are non-periodic, and thus period and frequency used for analog signals are not appropriate characteristics for digital signals. So we use another term that is called the bit rate instead of frequency to describe digital signals. The bit is the number of bits sent in 1 second expressed in bits per second, or BPS. Let's look at the previous figure again. Here we have the figure shows the bit rate for 2 signals. We have 8 bits per second on the left, and as 8 bits were sent, and we have 16 bits per second on the right, as 16 bits per hour sent in a second. Okay, let's do an example together. Assume that we need to download text documents at the rate of 100 pages per second. What is the required bit rate of a channel? Assume that we have a page is an average of 24 lines with 80 characters in each line. Okay, so there's no specific equation for bit rate, but in general, we can generalize bit rate as frequency multiplied with bit depth multiplied with channels. Frequency could be in terms of frequency or sampling rate, and channels, it depends if there's only one channel. If it does not specify more than one channel, then we just multiply with 1. Okay, so if we assume that one character requires 8 bits, and we can calculate the bit rate. Okay, because in any typical character, especially like for example ASCII ASCII code, we have one character which require 8 bits, right? So let's just assume that. So we can calculate as 100 times 24 times 80 times 8, where 100 is the samples per second or the sampling rate, and 24 multiplied with 80 is the symbols per sample per page. Okay, what is the number of bits of that? And of course you have to multiply with bits per symbol. Okay, just now the whole symbols per sample, and then okay, this unit at the bottom, it helps you to see whether you got the bit rate right or wrong, because otherwise you might have missed one step. Okay, so in this case the bit rate, which is supposed to be the unit of bits per second, is 1.536 megabit per second. Okay, all right, let's do another example. Okay, let's do example 2. In this example, it says that a digitized voice channel is made by digitizing a 4 kilohertz bandwidth analog voice signal, which you will see in the next chapter. Okay, we need to sample the signal at twice the highest frequency, which is 2 samples per hertz. Okay, so this is the sampling frequency. Okay, you need to have twice the highest frequency, which is the 4 kilohertz. Okay, and then we assume that each sample requires 8 bits. Okay, so what is the required bit rate? Again, so we can calculate the bit rate as multiplying 2 times 4000, which is the sampling rate, and multiply with 8 bits. Okay, so in this case there's only one channel, so we multiply with 1, but it's not here. Okay, and then it will be equal to 64 kilobit per second. Again, be careful with the units. Okay, you can check it here. So 2 times 4000 is the samples per second, because when we talk about hertz, it's the unit per second, right? And then we have 8 bits, which is bits per sample, because here you can see, assume that each sample requires 8 bits, which basically means 8 bits per sample, and then you get the bit per second, which is the unit for bit rate. Okay, next let's go to the next digital signal characteristic. Okay, so we have bit length. Okay, so for example, in analog signal, there is a concept that is called wavelength, which is the distance one cycle occupies the transmission medium. Again, this is similar but for digital signal. Okay, so it is called the bit length. The bit length is the distance one bit occupies on the transmission medium. Okay, so for bit length, we have equals to propagation speed multiply with bit duration. Okay, so you will need to have this information. Like for example, typically we have 2 times 10 to the power of 8, and we have, in this case, let's say that the bandwidth is 1 megabit per second, so the bit duration is the inverse of the bandwidth, and we'll get 1 over 1 times 10 to the power of minus 6, which is 1 microsecond. Okay, so let's see, with this kind of example, we have propagation speed of 2 times 10 to the power of 8 and bit duration 1 microsecond. What is the bit length? So the bit length can be calculated as 2 times 10 to the power of 8 multiplied with 1 over 1 megabit per second, and you'll get 200 meters. So you can see here, if you increase the bandwidth, that means the bit duration would be smaller, right? And that means that it is also proportionate to the bit length. So if you increase the bandwidth, and the bit length will also goes smaller, or it will be shorter. Okay. All right. What does it mean by 200 meter? It means that one bit occupies 200 meter on a transmission medium. Obviously, that is not very practical. So that's why we need to have a better bandwidth. Okay, we always want better bandwidth. With better bandwidth, then the bit duration will be smaller. Hence, the bit length will also be shorter. Okay, let's move on to transmission of digital signals. Okay, for this course, let us consider the case of non-periodic digital signal, which means that a decomposed signal has a frequency domain representation with an infinite bandwidth, and the frequencies are continuous. Okay, this is what we see in data communications. Okay, so the fundamental question is, how can we send a digital signal from point A to point B? We can transmit a digital signal by using one of the two different approaches. One is called baseband transmission, and the other is broadband transmission. And the latter one, the broadband transmission, is basically you have to use a modulation. Okay, so baseband transmission means that we are sending a digital signal over a channel without changing the digital signal to an analog signal. So the figure on the left shows baseband transmission. A baseband transmission requires that we have a low pass channel, a channel with a bandwidth that starts from 0. Okay, so that is why it's low pass. Basically is, right? So in this case, we have a dedicated medium with a bandwidth constituting only one channel. Okay, for example, the entire bandwidth of a cable connecting two computers is one single channel. Okay, another example, we may connect several computers to a bus, but not allow more than two stations to communicate at one time. So again, we have a low pass channel and we can use it for a baseband communication. Figure on the right, it shows two low pass channels, one with a wide bandwidth and the other with a narrow bandwidth. We need to remember that a low pass channel with infinite bandwidth is ideal, but we cannot have them in real life. Okay, so but we can get as close as possible. Okay, so baseband transmission of a digital signal preserve the shape of the digital signal only if you have a low pass channel with an infinite or a very wide bandwidth. Okay, and in bandwidth transmission, the required bandwidth is proportional to the bit rate. If we need to send bits faster, then we would need more bandwidth. Let's go to the second approach of digital signals transmission. It is called broadband transmission. Broadband transmission or modulation means changing the digital signal to an analog signal first before transmission. Modulation allows us to use a bandpass channel. Okay, a bandpass channel is a channel with a bandwidth that does not start from 0. This type of channel is more available than low pass channel. You can see the bandpass channel on the top figure. Actually, please note that low pass channel may also be considered as a band pass channel, but with a lower frequency starting at 0. Figure on the bottom shows the modulation of a digital signal. In the figure, we can see a digital signal is converted to a composite analog signal. We have used a single frequency analog signal called a carrier. The amplitude of the carrier has been changed to look like the digital signal. The result, however, is not a single frequency signal, it's a composite signal, combination of a few signal elements, and at the receiver, the received analog signal is converted to digital, and the result is a replica of what has been sent. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.